Welcome to the second part of the talk, volume of a random canonical lift. So in this second talk, I will be giving a sketch of the proof of the main theorem that I introduced in the previous talk. So here's the statement again. So again, this is joint work in progress with Yannick Rivka, Tom Kromasky, Franco Vargas-Payette, and myself. And we show that if you look at a closed parabolic surface X and a pair of pairs decomposition, and consider the primitive element corresponding to a random closed geodesic as constructed in the previous talk, then there are constants A and delta between 0 and 1, where delta can be made arbitrarily close to 1 by changing X and P, so that you get the following lower bound of the volume of the random canonical lift. The lower bound depends on a function f of t. F of t is a sublinear function of the type t over w of t, where w is the Lambert function. The Lambert function is asymptotic to the logarithm of t minus the logarithm of t plus smaller 1. So that's the statement, and again, there is this extra exponent here that we have to raise this function of t to this delta again can be made arbitrarily close to 1. And so let's start with the sketch of the proof. So the proof proceeds in 3 steps. So the first step is dynamical. In the first step, we will do the counting. We will count the number of arcs of the closed curve that we obtain when we build this random closed geodesic. So if you remember, the random closed geodesic was obtained by pulling tight a curve that was constructed by following the geodesic flow for a very long time t, and then closing off by a short segment. Well, let us distinguish this closed curve that we have before pulling tight and the corresponding closed curve and its primitive element. So we will be looking at 2 curves here. So one will be the curve gamma TB, which will be the closed curve constructed in the random model. And then, so when we construct this curve by following the geodesic flow and then shortcutting, then we can pull tight to obtain the corresponding geodesic representative. And then we can, moreover, take the primitive element of that geodesic representative, if it's not primitive. Okay, and that curve, we will call it, we will distinguish it by a superscript P. Okay, so in this first step, we'll be looking at the closed curve as opposed to the geodesic primitive. What we can show is that there are constants A and B between 0 and 1. Again, B will be playing the role of the constant delta in the previous statement, that give a low, so that we have the following lower bound for t long enough. Okay. So we have the following lower bound for the number of gamma t v arcs. Okay, so this is the closed curve constructed in the random model. And this is going to use dynamics. In particular, is going to use the exponential mixing of the geodesic flow. And then some analysis, because to apply the exponential mixing, which is a result that, in fact, will be an independent result that we will prove in this project, we need to approximate the volume of the maps BI by smooth functions, by smooth bound functions. So in the rest of this talk, I will be focusing in more detail on this first step. But now let me go to step 2 and give you a quick idea on how step 2 of the proof proceeds. So once we have this lower bound on the number of gamma arcs, then we would like to see what happens with the corresponding primitive geodesic, right? So the danger here is that when you pull tight to get the corresponding geodesic representative, the number of gamma arcs might drop or might change considerably. So what we can show is that in fact this doesn't happen. Then the number of gamma arcs that you get, if you consider the closed curve that you get by constructing the random curve by following the geodesic flow for a long time and then shortcutting, is actually very close. You know, at most it can drop by 1, in fact, to the number of gamma arcs for the geodesic, for the primitive geodesic representative. And this argument uses some hyperbolic geometry estimates to show that this pooling tight homotopy is actually short, and also requires, on top of that, some topology to analyze the types of bigons that can occur for this particular closed curve in order to establish this result, that the number of arcs actually doesn't change a lot when you pull tight. So I will not get into details in this step 2, but once you have these 2 steps, then you're essentially bounded the number of arcs, of gamma arcs for this primitive geodesic, and we also know it's filling because this gamma, the original closed curve, gamma is filling, and the property of being filling does not depend on the representative. And so as a result, we can apply the lower bound by Rodriguez-Migueles, and we obtain this lower bound on the volume, okay, and giving us the result of the theorem. Okay, so these are the 3 steps. Let me focus a bit more on step 1. Okay, so how do we do this counting of the number of gamma arcs, or how do we do this? Do we get this lower bound? So we will be looking at orthogeodesics in a given pair of pans. So here's 2 examples of orthogeodesics connecting the same 2 boundary components. So you have this simple orthogeodesic connecting this boundary component to this one, which is colored in red, and you have another orthogeodesic, which is different, that we call little oj, which also connects the same 2 boundary components. And what we will do is we'll rank the orthogeodesics, not just in this pair of pans, but among all pair of pans by the length. Okay, so we will denote L sub I to the length of the of the ith orthogeodesic, where this ith is we ordered the orthogeodesics by length. Okay, and as we run over all the orthogeodesics for all the pair of pans in the pans of composition. After we give this order, we can actually consider the following set BI, the set BI of points in the unit tangent bundle of the pair of pans PI. So PI is a pair of pans containing OI. And we can look at all the points V in this unit tangent bundle of the pair of pans PI with the property that if you intersect the corresponding geodesic gamma V generated by the point V, so here's your point V in the unit tangent bundle, is the unit tangent bundle of UTPI, of PI, so the unit tangent bundle of PI. You pick a point in the unit tangent bundle, so a point and a direction, and then you consider the geodesic that is inside of this pair of pans PI, and it's generated by this point in this unit tangent bundle of PI. Well, this geodesic, this particular blue geodesic, is freely homotopic to this orthogeodesic, this red orthogeodesic. And so because of that, we say that this point B is in VI. Okay, so that's the set of points VI satisfying this property that their corresponding geodesics are freely homotopic to the orthogeodesic OI. And the good property about these sets VI is that in fact, they give a partition, can partition the unit tangent bundle as a union, as a disjoint union of these sets VI together with another set, let's call it M sub 0, that we will just disregard because its Liouville measure is actually 0. Okay, so the good thing about these VIs is that we can partition the unit tangent bundle of X as a disjoint union of these VIs. And if you look at these VIs in the universal cover, they actually have a nice parameterization. Okay, so here's how you can parameterize them. So you can look at the lift of the orthogeodesic, the red orthogeodesic in the previous picture. That's so that it corresponds to the vertical axis in the upper half plane. And let's suppose that this inner semicircle, it corresponds to the lift of this boundary component, whereas the other bigger, the outer semicircle corresponds to the lift of the other boundary component. And then a point is in VI. If you look at the corresponding point in the universal cover, its lift lies between, well, it lies between these two semicircles. So in this semicircular strip, and the endpoints of its of the intersection of the corresponding geodesic gamma V with these semicircles are located in these semicircles. Okay, so if you pick a point here and the corresponding and the corresponding geodesic intersects the corresponding semicircles. Okay, so that's a nice parameterization of this set BI. Using this parameterization, we can actually compute the Liouville measure of this set's BI. And we can actually give an explicit asymptotic formula given in terms of this. This uses some results by Bridgman. And moreover, we can also relate the length of the ith orthogeodesic to its order. So we can actually, at least asymptotically, relate the order in this ranking of orthogeodesics to its length. This follows by a result by Martínez in 2018 that gives you the number of orthogeodesics up to a given length. So this is the relation between Li and the corresponding I. Here, delta is the Hausdorff dimension of the limit set of the pair counts Pi that you're considering. And so putting these two things together, we can relate the measure of the set Bi to the number of arcs, or in other words, to the number of orthogeodesics, because we are counting arcs here up to free homotopy. Now let's relate the whole picture to the dynamics. So let's consider the unit time flow map. So what is the unit time flow map? Is the map that goes from the unit tangent bundle of X to the unit tangent bundle of X, and to every point in the unit tangent bundle, it assigns the point that you obtain when you travel for time 1 following the geodesic flow. Okay, so here again, GT is the geodesic flow. So this gives us a dynamical system, a discrete dynamical system from the unit tangent bundle to the unit tangent bundle, and we'll define C sub n of V as the number of different BI sets that we visit in this partition as we iterate the unit time flow map. Okay, so consider n steps, big n steps of the unit time flow map, and you will get points V, T of V, so on, T of n minus 1 of V. You get n different points in the unit tangent bundle, and then among those, you want to see how many correspond to different VI sets. So how many different VI sets have you visited as you've moved from point V to point T n minus 1 of V? Okay, so we define this set C sub n of V in this way. Now, this is keeping track. If you remember, each set VI corresponds to a orthogeodesic order I. And so it's keeping track of the free homotopy classes of gamma arcs. So let's consider a picture. So here's the picture, simplified cartoon of the unit tangent bundle. And here's our initial point. Let's pick an initial point here, V. Is this red dot here. We apply the unit time flow map, we get to TV. So initially our point V was in some region, which is colored in this pink over here. This region is some set BI. Let's call it BI sub 1. And then we apply the unit time flow map, and we land in this other new region, which corresponds to another set BI interpretation. Let's call it BI sub 2. And we keep doing that, and time T2V, we will end up in some other set BI sub 3, and so on. If you notice, then in T4 we get here, T5 and T6, they both happen to be in the same region, in the same BI region. So these two are in the same set. Let's call it BI sub 4 or BI sub 5. And so we keep going, and we follow this green path corresponding to our trajectory in the geodesic flow, and we are sampling a discrete set of points in that trajectory corresponding to the unit time flow map. And as we move along this trajectory, this unit time flow map keeps visiting different BI sets. And we are keeping track of how many different BI sets we are visiting up to time n. So here, let's suppose that this is the nth step. So here's the point Tn, T super n of d, okay, or minus 1 as before. So up to time n, how many different VI sets have we visited? So, for example, if we this is C sub n is the number of different VI sets that we have visited. And we would like to visit enough BI sets. So a number of distinct BI sets are larger than some growth rate that we will call M. In fact, what we want to find is the growth rate M, depending on N, depending on the total length of this iteration, so that the number of visited BI satisfies that the probability this is mu, is again, remember the normalized Liouville measure in the unit engine model. So the probability that the number of distinct visited sets is larger or equal to M, so that we visit at least M distinct BI sets, goes to 1 as N goes to infinity. Okay, so we want to find some growth rate depending on this total number of steps such that this probability goes to 1. Okay, so as we let the flow go to infinity, we end up visiting with high probability a number of distinct sets that's larger, at least as large as this growth rate, and with probability 1. So what we can prove is that, in fact, if we take this growth rate to be a function depending on n in the following way, so as a function depending in terms of the function f that we have introduced before. Remember, this was a function of the type f was a function of the type t over the Lambert function of t. Okay, so here, of course, the variable should not be t, but instead should be n, the normal discretization of t, the number of total steps. So if we take this growth rate, then we can guarantee that the number of this probability goes to 1 when n goes to infinity. Okay, so this is going to be the goal to prove, to connect this whole discussion to the dynamical picture. Okay, so we perform a discretization process where we use the unit time flow map. And so how do we take care of this? How can we actually estimate or give a lower bound to this probability? Well, what we can do is by actually writing out what this probability is. So we can actually write down, or at least give a lower bound to this probability. By playing with probabilities a little bit, we can get to the following lower bound that depends on sum of probabilities of the intersection of the push forwards of the unit time flow map or the complements of the sets BI. Okay, so this is just some mouthful, but the point is that by playing with these probabilities, we can get to this expression. So giving a lower bound to this amounts to giving an upper bound to this other probability, right? So because this set is the complement of this. And now the point is to try to estimate what this upper bound is, which is a sum of probabilities coming from these intersections. Okay. So in fact, and here's where mixing and the strong dynamical properties of the geodesic flow will play an important role, because thanks to mixing, what we can do is we can get rid of these pullbacks here of the in-time flow. So here's what we can do. So first of all, in order to apply a mixing theorem, one has to approximate these probability measures, which are volumes, as integrals of sufficiently nice bump functions, so smooth bump functions. And of course, one has to be very careful in these approximations. And the reason is because in the theorems that we will apply, the error term, so the goal is going to be to estimate this term, a term like this, in terms of the volumes, in terms of a term that does not depend on these pullbacks of the unit time flow map. And the difference between this term and the term that does not depend on the pullbacks is some error. And that error depends on how good this approximation of these volumes is. So the first step is going to be to find good approximations. So to write the probability of these sets, these intersections, as an integral of some indicator function, and then approximate each one of these characteristic functions by bump functions that we can construct explicitly and that we have sufficient control over. And then the point is going to be, the point of this approximation is going to be that then we will be able to actually estimate this term by using a mixing theory. So here's what I was talking about when I was saying mixing result or strong property, mixing properties of the geodesic flow. I mean a result of this kind, a result that tells you that if you want to estimate an integral like this, depending on the integral of several bump functions on the unitangent bundle, restricted to some sets. In this case, the support of these bump functions is contained in the sets BI. As you take iterates of this unit time flow, okay, so you're precomposing these bump functions with iterates of this unit time flow map, which is what is happening here in the term that we want to estimate. Well, you can actually estimate this volume by the similar integral where you don't actually take into account these translations by the unit time flow map, and you just consider the integrals of the bump functions alone, which is a term that's much easier to compute because it's just a product of integrals that are very close to the corresponding volumes of the VI sets, which we actually know how to compute. But of course, in order for this estimation to hold, to give you any useful information, you will have to control this error term here, okay? And so that's going to be the next goal. Okay, so our goal, just to recap, is to show, in fact, that because we want to show that we want to give a lower bound to this probability, which means we would like to estimate this term. What we would like to show, indeed, is that we like to show that this goes to 1 as n goes to infinity, which amounts to showing that this term goes to 0, this term goes to 0 as n goes to infinity. And by translating it into the language of bump functions, it means that we want to show that this term goes to 0. But to show that this term goes to 0, it is enough to show, because of this theorem, that this term goes to 0 and the error also goes to 0. Okay, so now our goal is to show that this term goes to 0 and the error goes to 0. This term we can estimate if we understand well enough these bump functions. And similarly for this error term. But there is an extra thing to take into account here. There is this extra term as here, as of phi k. So whereas this term only depends on the integral of these bump functions itself, this term, this error term, this as of phi k, depending on the bump function k, actually depends on the higher order derivatives of these functions phi k. So we really need a very precise control on these approximating bump functions. And so that the technical part of the proof is to actually show that we can actually perform these approximations in a controlled enough way so that we can ensure by picking a convenient choice of n that this term, as n goes to infinity, goes to 0, and so does this other term over here. So to give you maybe a more precise idea of what we do is, instead of looking at the unit time flow, we allow ourselves an extra slack, and we look at the L time flow. So instead of taking unit time flow, we consider the flow up to some higher iterate L. So the way we do this, well, we were considering this so number of big N steps in our dynamical system. Well, we let N be very large, and we divide the iterations by a smaller number N, and look at the essentially asymptotics of the type N being equal to L times N. Okay. And so what we would like to do is we would like to let this small n go to infinity, where when an L, and let L be fixed. So instead of like looking at each unit time flow iteration, we are spacing out these iterations and looking, for example, at L equal 4 iterations. So here's the first iteration for L equal to 0, here's for L equal to 3, and so on. So we're only looking at the blue ones. Okay. And by allowing ourselves this extra slack, this is a useful technical condition that we can do. But then the point is that by using these approximations and by then seeing what are the necessary conditions that we need to impose on this n and on these approximations in order for this term to go to 0, this term corresponds to the integral of the bump functions, and this other term to go to 0, this term corresponds to the error term in the mixing theorem. So by making a convenient choice of n and a convenient choice that is well suited with respect to these approximations, we can guarantee that these two terms go to 0, and therefore the term, the probability that we wanted to estimate, also goes to 0, so that its corresponding complement probability goes to 1. And so that concludes with the theorem. Now, the technical part of the proof here is going to be to actually study this mysterious term as of p that depends on higher order derivatives of the bound functions. Okay, I'm not going to get into these terms, and I'm not going to say the word. Well, at least I'm going to say the word. It's Sobolev norms, but to get into the details of this would require much more time. So I'll be happy to discuss if anybody has questions about the details of this technical part of the proof during the office hour session. Well, I will finish my talk here, and thank you for your attention. Let me remind you that my office hours are going to be June 16, 2 p.m. and Eastern time, and June 21st, again, 2 p.m. Eastern time. I'll be happy to discuss any of this with you through Zoom and in a more interactive way. See you there.